Our next speaker is David Plotkin, who studies earth sciences at the University of Chicago. His advisor is Dorian Abbott, and his practicum was at Argonne National Laboratory.
Sweet, thank you. Cool, is this working? Oh, it is, that's loud. All right, so I'm going to continue with the previous two themes of avoiding HPC and work in progress, so I hope you guys forgive me that. I'm going to talk to you guys about simulating tropical cyclones in a climate context, specifically with a method called action minimization. So the first question you might reasonably ask is, why should we want to simulate tropical cyclones, specifically in a climate context? And by climate context, I mean we're not just trying to predict what the weather is going to be like tomorrow or what a individual storm will do and where it will go, but more trying to understand the long-term behavior of cyclone intensity distributions. So the main reason that we might care is that there's some compelling evidence, or at least compelling physical intuition, to think that cyclones may become more intense as a result of global warming. The very schematic physics here is that cyclones are powered by latent heat, that is to say water vapor that evaporates from the ocean. So a warmer ocean means a warmer lower layer of the atmosphere. A warmer lower layer of the atmosphere can hold more water vapor, so there would basically be more water vapor available to power cyclones. I'm also going to use cyclones, hurricanes, typhoons, etc. interchangeably. Those all refer to the exact same thing. So this figure shows an ensemble of simulations from climate models. The left panel shows simulations with a present-day climate, and the right panel shows simulations from a future warmer climate according to one of the IPCC scenarios, International Panel on Climate Change, that is. I'll try to avoid acronyms, pardon. So the vertical axis here is the minimum surface pressure of the cyclone. So the stronger the storm, the lower the surface pressure. The horizontal axis is the maximum surface wind speed. So stronger storms are down and to the right on the plots. So, and as you can see, the cyclones in the warmer climate, you get more strong storms. You get more storms in the lower right portion of the plots. However, you have to take all of this with a bit of a grain of salt, because we can't really even do a good job of replicating cyclones in the present climate with our models. We can't really match the data. So this, again, is a plot of maximum wind speed versus minimum sea level pressure. And the black line and the black dots here are data. The colored dots are various models from more or less from increasing resolutions going from left to right. And as you can see, all of the models consistently underpredict the maximum wind speed. So we can even get unrealistically low sea level pressures, but we can't do a reasonably good job of matching the strongest surface winds for the strongest storms. And that's really what we care about being able to predict, because storm damage is highly nonlinear, wherein the very few strongest storms cause by far the most damage. And specifically, the reason that we do a really bad job of simulating very intense storms is that we fail to capture a process called rapid intensification. So this is the process that differentiates strong cyclones from kind of run-of-the-mill tropical storms or smaller hurricanes. In rapid intensification, you get a storm that maybe doubles or even triples in intensity, that's to say in maximum wind speed, over the course of 24 to maybe 48 hours. So again, here we have a plot of a specific storm, just the maximum wind here over time. And the black curve and the black points are, again, observations. So here you can see that between, say October 22nd and 23rd, this particular storm intensified by a factor of maybe 3 or 4. The maximum wind increased by a factor of 3 or 4. The colored curves are a bunch of different models started at a bunch of different points along the storm's trajectory. Notice that none of them have this show the signature of rapid intensification. So our models do a reasonably, and there are plenty of storms that look like the modeled storms, but no model can capture storms that do in fact exhibit rapid intensification. So in part, the reason that we can't do a good job of capturing rapid intensification is that there are a bunch of sort of putative mechanisms for why this happens, and we don't actually understand how much of a role each mechanism plays, or if some of them are just outright wrong. So I'm going to kind of briefly overview two general families of rapid intensification mechanisms. The first is one that I would call convective feedbacks. So in this figure, the horizontal axis you can think of as the distance from the center of the storm. The vertical axis on the left is just height in the atmosphere at the center of the storm. So if you were to take this figure and rotate it around the vertical axis on the left, you would get a full symmetric storm, which is, to first approximation, not a bad way of thinking about a tropical cyclone. And the arrows show the direction of the circulation or of the wind. So you get rising air in the center and air that converges towards this from the outside of the storm to the center along the ocean surface. So the first feedback is called wind-induced surface heat exchange, Wishy for short, where you have this converging surface wind causing evaporation. So the wind is picking up water vapor. This water vapor in turn powers the convection. This strengthens the storm. This increases the surface wind, so on and so forth. There are other similar feedback mechanisms like CISK, but they're fairly similar, and I don't want to get into them for the sake of time. The second class of intensification mechanisms I would broadly term organized convection. So an example of this is vertical hot towers, where you could have a geographically large but fairly weak in terms of intensity storm, and through processes such as turbulence, you could get the formation of rapidly rotating hot towers, quite small. And then because of the low pressure at the center of the storm, these towers would get drawn in, they would merge, and then through conservation of angular momentum, the storm would intensify. So, and in fact, there's kind of an amusing controversy and back and forth over these mechanisms. If you remember, the acronym for the first one is Wishy, and the people who are advocating this mechanism have written papers citing the Wishy mechanism and so on and so forth. So this is very far from resolved, and it's actually hard to get at this question with models for a few reasons. In part, we're just limited by resolution. Most climate models have horizontal resolutions of maybe 10 or tens of kilometers. In order to capture the fine structures at play in tropical cyclones, you really need to capture things like convection, things that happen on a scale of under a kilometer. So we're just limited by resolution. You also necessarily have to parameterize some subgrid processes. You can't, you can't include cloud microphysics, which happens on, like a scale of nanometers in a climate model. So these parameterizations are built to work at kind of normal weather conditions. They don't work so well in extreme conditions, such as in a cyclone. And we also just have small sample size in that really strong storms are rare. So if you run a climate model for 10 years of model time, you might see one Category 5 hurricane. So you're just going to be wasting a lot of time simulating states that you don't necessarily care much about. There have been a few kind of strategies to circumvent this, but I think the most common one is just brute force. We wait on more computing resources to become available and crank up the resolution. And this is kind of a very slow process, and I think it will take quite a while with this specific problem. So what I've been working on, or my group has been working on, is trying to actually avoid some of the computation and reduce the cost of getting models to form strong cyclones. And we're doing this using an algorithm called action minimization, I think borrowed from molecular dynamics largely. So the benefits of this are hopefully twofold, in that we reduce the computational time it takes to form storms, and we also actually automatically get the model to select likeliest mechanisms for storm formation. So schematically, the way that action minimization works is that you have a model that has some native deterministic dynamics that we fully understand. We'll, for now, say that it models the physical world. And then we want to add every time step, or once every several time steps, we add little perturbations. You can think of them as small noise, in order to try to get the model to go into some specific state or set of states that we care about simulating. So in this case, in the schematic, we have a 2D dynamical system. The normal deterministic model dynamics are shown in blue, so the blue arrows, and the perturbations are shown in red. So if xk is the state at time step k, the model will want to integrate to f of xk, or I guess here I had xk minus the state xk minus 1, and the model dynamics want to take it to f of xk minus 1. However, we add a little perturbation at that next time step that's labeled xk minus f of xk minus 1. So through a series of such perturbations, we can take a model trajectory that would maybe not have gone into the set of states that we care about and instead direct it to a particular set of states. In this case, the state that we're trying to aim at is something that contains a tropical cyclone. So a little bit more formally, we can write this as a minimization problem. The first term just says that we want to start our trajectory near some initial condition. That's not particularly interesting. That middle summation is a summation over all time steps, and it's a summation of the squares of the perturbations. So basically, we want to minimize that. So we want to add as small perturbations as we possibly can. We don't want to mess with the model physics too much. Then we're going to get stuff that's just unrealistic, that doesn't behave in a physical way. This is, I think, the way it's written right now, it's for a 1D system, but this generalizes easily enough, because we have something like a 10 to the 9th dimensional system, I want to say, for climate problems. So we minimize the sum of the perturbations plus some function that measures hurricaneiness, which is definitely not a word. So basically, this function g of xn is some function of the final state that could be small if we're in a strong hurricane and large if we're in calm weather. For instance, the simplest version that I've been using is just the minimum surface pressure, since in a strong hurricane you have low surface pressure. So the more hurricaney the final state, the smaller g will be. So we just minimize a weighted sum of how close we are to a hurricane at the end, plus the perturbations that we had to take in order to get there. If you do this, especially if you do this in an ensemble kind of way where you pick multiple initial conditions, you can actually think of this, of the resulting trajectory, as selecting the likeliest paths by which the model would want to form a hurricane. So the output of this minimization is basically a trajectory. So we get a sequence of weather maps, say a weather map for every hour for a week, that goes from calm weather to a hurricane. In doing so, we can basically form a hurricane within 1 week, as opposed to having to wait for, say, 10 years to form a Category 5 storm, which is a benefit. And we also, again, try to solve this problem in a smart way, or frame this problem in a smart way where we actually can select where the solution turns out to be the likeliest mechanism of hurricane formation. This turns out to be kind of a nasty and poorly conditioned problem. It also, you need the gradient of f, the gradient of the model flow, which is something that doesn't really exist save for 2 climate models or weather models. One of them is proprietary, so really there's only one model, the Whorf model, which I guess maybe like one person in here has worked with, which is really, really terrible. So actually getting it to just behave well and give back all the needed derivatives and so on has been taking me about the past year. So unfortunately, I don't have really a ton of very pretty pictures to show you. We do finally have the code working, and it does so for now at far too low resolution to really make any interesting statements about how rapid intensification is occurring. But it does seem to create more or less physically realistic hurricanes. And there is some amount of rapid intensification going on, even though it is somewhat slower and less intensifying than in observed hurricanes. So the output that we get from this problem looks something like this. So this is a map of the minimum pressure. Our domain is actually built so that it tracks the storm and follows it around. The hope is to be able to use this, first of all, just at much higher resolutions. If we have the computing resources to do it at resolutions that are fine enough to resolve things like convection that we really need to honestly model storms, then also to use this to create a Monte Carlo algorithm where we can actually do ensemble simulations in different climates in a much more computationally efficient way, since we won't be having to wait around tens and tens of model years for strong cyclones to form. So with that, I would like to thank my advisors at UChicago, Dorian and John, and of course the DOE CSGF Fellowship. And I will take questions.